Okay, so this is the discrete time counterpart of Laplace transform. If you remember, the motivation for why we need Laplace transform is that many signals, if we consider a continuous time signal xt, the condition for existence of Fourier transform is this one. It is the signal must be absolutely integrable. That is for a continuous time signal. Then we can say that the continuous time Fourier transform of that signal exists. And many signals that we have seen that many signal doesn't have this. Many signals are not absolutely integrable. So we cannot have a Fourier transform. That's why we discuss Laplace transform, which is, we can say that it is in more generalized sense. Many signals that doesn't have Laplace transform can have a that doesn't have Fourier transform can have a Laplace transform representation. Same with discrete time signals. The condition for existence of discrete time Fourier transform. Okay. Discrete time Fourier transform of a signal is defined as xn. Its Fourier transform, we denote it by x of e to the power j omega, that is summation over n xn e to the power minus j omega n. This is the discrete time Fourier transform. And the condition for existence of this discrete time Fourier transform is, what is the condition? Here, continuous time signal, it is absolutely integrable. In the case of discrete time signal, the condition is that the signal must be absolutely summable. This is the condition. Okay. The signal must be absolutely summable, and many useful signals doesn't have this property, like they're not absolutely summable. For example, if you consider a unit step sequence u of n, this is not an absolutely summable sequence. So its Fourier transform does not exist. And we have seen that in the generalized sense, for this particular case, unit step function, we can have a Fourier transform representation, but that is not in the true sense. And some other signals, like let's say, if we consider a ramp signal, which is defined as R of n, that is, let's say, n for n greater than or equal to 0, and 0 for n less than 0. Consider this signal. It is not an, it is a growing signal. As n tends to infinity, its amplitude tends to infinity. So it is not an absolutely summable signal. So Fourier transform does not exist, isn't it? And so if we have a discrete time signal xn, its Z transform, it is, let's say, it is defined as is it the form of Z transform you have studied in your mathematics course? Is it the same form?
So we had learned one-sided.
One-sided from 0 to infinity only, isn't it?
Yes.
Okay, so we'll discuss about this is called the bilateral Z transform. We'll discuss about this. And anyway, unilateral Z transform is a special case of this only, when this is the summation is from 0 to infinity. Okay, so this is how we define the Z transform. It is the bilateral Z transform. Now, what is the condition for existence of this? Okay, first of all, let's see how it is related to the discrete time Fourier transform. The discrete time Fourier transform is, this is the definition. Isn't it? This is the definition of discrete time Fourier transform. So how are they related? Can we write it as a special case of the Z transform of the signal. Is it this? It is a special case of Z transform when Z is e to the power j omega. Okay, let us discuss more details about about this in more detail. When we consider Z is a complex variable, and if we write it in the polar form, and I hope you remember the polar representation of complex numbers. If we consider a complex plane, this is called the, let's say in this case it is called Z plane, and this is the, okay, so there is some issue here. Let me draw it here. This imaginary axis, real axis. This is called the, okay, and we take the polar representation of that complex variable in this case because of this discrete variable n. And in the case of Laplace transform, we considered S as sigma plus j omega, isn't it? But here we consider the polar form. Okay, now let us see what is the relation between the Laplace discrete time Fourier transform and Z transform. So if we, okay, let me take a new page. X of Z is summation n from minus infinity to, this is the definition. And if we consider then X of Z is tell me what is the relation? Z transform of a signal xn, that is equal to what? Fourier transform of, what is this summation? Is it the Fourier transform of xn into r to the power minus n? If we have a signal x of n, its Fourier transform is summation n from minus infinity to infinity xn e to the power minus j omega n. So here Z transform is this summation. So can we say that it is the Fourier transform of the signal, or I'm writing it as discrete time Fourier transform of the signal xn r to the power minus n?
Yes, sir.
It is the transform of the signal xn, that is the discrete time Fourier transform of the signal xn into r to the power minus n. Okay, where r is, you consider z is a complex variable, that is we are writing it as e to the power j omega. Okay, and in the complex plane, that is if we plot this z, if you consider a point here, this is r, and this angle is what? This angle is
Omega.
it is omega. Okay, so it is discrete time Fourier transform of the signal xn into r to the power minus n. Now, what is the condition for existence of Z transform? If you are given a signal xn, its condition for existence of Fourier transform of that signal is the signal must be absolutely integrable. Now, if the Z transform is the Fourier transform of xn into r to the power minus n, what is the condition for existence of Z transform?
X and R to the power minus n
It is-
is summable.
This must be summable, isn't it? And why are we writing like this? Because r is greater than 0, isn't it? R is greater than 0, so we write like this. So this is the condition for existence of Laplace Z transform. If you consider any point in the Z plane, let's say you consider a point here, the condition for first of all, consider a signal xn. If you want to evaluate the Z transform at any point in the some point Z, then the condition for existence of Z transform at that particular point is, this is R, xn, this must be absolutely summable. Okay, so that is the relation. Now let us discuss about the ROC.
Excuse me, sir.
Yes.
So you said that Fourier transform and Z transform are equal when
Mhm.
Z is equal to e raised to j omega.
Mhm.
So that means R is all that magnitude of Z is always 1, right?
Magnitude of Z is 1. Okay, first let us discuss that. X of Z is and x of e to the power j omega is isn't it? So what I said is when Z is equal to Z is R e to the power j omega, when Z is e to the power j omega, then these two are equal, isn't it? This Fourier transform is a special case of Z transform. That means when R is 1. What does it mean? If we want to find the Fourier transform of the signal, let's say at some value x e to the power j omega naught. Where is this point in the Z plane? You want to find this Fourier transform of a signal for some frequency omega naught. Then can you tell me where is that point? How is it related to the Z transform? Where we have to evaluate Z transform?
Where Z is equal to e raised to j omega naught.
When you have to evaluate that Z is equal to e to the power j omega naught. Where is that? Is it,
Yes, sir.
there is a, what is the length of this?
1.
1, and this angle is omega naught. So you have to evaluate Z transform at this point. That is the Fourier transform of the signal omega naught at frequency omega naught, isn't it? Okay. Now can we say that if you want to find the Fourier transform at some other point, let's say omega 1, and let's say this angle is omega 1. Omega 1. So is it at this point? So can we say that the Fourier transform is the Z transform evaluated where?
In this circle.
In the unit circle. This is called unit circle. That is okay. That is we can say that the Fourier transform is the Z transform evaluated in the unit circle. And what is the relation in the case of Laplace transform? What is the relation between Laplace transform and Fourier transform? Where was it evaluated?
S
X
is
of,
equal to j omega.
where S is sigma plus j omega, isn't it? So in the case of Laplace transform, it was Fourier transform is the Laplace transform evaluated along the j omega axis. So here there is a difference. It is along the unit circle later on. Okay. Now let us discuss about the ROC of this Z transform. The condition for existence of Laplace Z transform is this must be absolutely summable. Mod xn into r to the power minus n, that must be absolutely summable. Now, if you consider the Z plane, what is region of convergence? Region of convergence is the region in the Z plane where this is valid. That means this summation, this converges. Or we can say that the Z transform is valid only for those values of Z where this is satisfied. Is it? Now, can you tell me what will be the shape of the ROC? In the case of Laplace transform, we have seen that the shape is vertical strips. What is the reason for that? In the case of Laplace transform, the condition for existence of Laplace transform is xt into e to the power minus sigma t dt. This must be finite. And in the S plane, what is that region? If you consider any point S here, can we say that if we consider any point along this vertical line passing through that point, that will also be in the ROC? Is it true? In the case of Laplace transform? Because sigma plus j omega, isn't it? Sigma is the real part. So all the points along this line will have same real part. Now tell me, what about the Z transform? Condition, the condition for existence, that means this converges. That convergence, that depends only on the value of R, isn't it? Can we say that if we consider a point Z, some point Z here, and if this summation converges, then can we say that all the points along the circle are in the ROC? If it converges at this point, can we say that all the points along the circle is in the ROC? What is the reason? If this is R, if you consider any point in the circle of radius R, that will have the same value, isn't it? It is also absolutely summable. So this is also in the ROC. Okay. So in the case of Laplace transform, the shape is vertical strips. And here we'll discuss that in detail. The shape of ROC for the ROC of Z transform for different types of signals. Those are rings in the Z plane. Okay. 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 Let us consider this sequence. X of n is here. Let us assume that a is greater than 0. What is Z transform? Is it this? Can we simplify this summation? Is it the Z transform of a to the power n Z raised to minus n? Sorry, a to the power n un.
Yes, sir.
And what is the condition for existence of this? What is the condition for convergence of this sequence?
Mod E by Z is less than 1.
Isn't it? That is the condition for convergence. So we can say that, is it this? Mod Z greater than A? Is it the condition for this convergence of this? Now tell me, what is
Yes.
the shape? So we can say that this Z transform of the signal a to the power n un that exists for all the values of Z that satisfies this condition. Tell me, what is the shape of that ROC? in the Z plane?
Outer part of the circle.
Outer part of the circle of radius. What radius?
A.
Outer, it is outside the circle of radius A, isn't it? Okay. That is the shape of the ROC. A to the power n, Z to the power minus n, and we'll see it see later on that how we get this. We can directly get the ROC from this Laplace transform. But is there any pole here? But
Z
it'll have
equal to A.
Z equal to A, isn't it? Okay. So there is a pole at A. Draw a circle through that, and it is outside that circle. And the next one is minus a to the power n u minus n minus 1. This is a left-sided sequence. Earlier a to the power n un, that is a right-sided sequence. This is a left-sided sequence. And if you find the Z transform of this signal, this is summation from minus infinity to, because u of minus n minus 1, it is non-zero in which interval?
So n less than equal to -1.
It is, so we can say that the summation is from, there is a minus sign here, a to the power n, is it this? It's a transform of this signal if this is x of n. Okay, can we simplify this? This is, we can write it as minus infinity to, let's say 1 to infinity. So can we write this as, okay, 1 minus summation, this is from n to 0 to infinity. Is it that? Here summation is from 1 to infinity. If you consider 0 to infinity, then there you have to subtract 1 because of this minus. It is 1 minus this term. And if you simplify this, you will get the same result as before. 1 upon 1 minus what is the ROC? ROC means
Circle of radius
this.
A.
Yeah, this must converge. This summation. The condition is that condition for convergence of this is isn't it? So what is the ROC? Is it mod Z less than A? This is the ROC, isn't it? If this is the condition for convergence of this this sequence, so this is the condition. What is the shape of that? What is the shape?
Inside of the circle.
It is inside the circle of radius A. That is the ROC. Again, is there a pole here? What is a pole?
Z is equal to A.
This is a pole. Okay. So draw a circle through that pole. Everything inside that is in the ROC. We'll generalize that later on. Okay. So here we have discussed two standard results. The first one is this one. It is 1 upon 1 minus a z raised to minus 1, and okay, this is the ROC. Here you can see that both these for both these signals, the algebraic expression for the Z transform is the same, but the ROC is different. Okay, so we have to mention the Z transform representation is incomplete without the ROC. You have to specify ROC.